Okay, for reasons I don't fully understand, my video just randomly cut out there. But we had the vector valued function for a circle. Want to do another problem? Number 3 on page 37 in chapter 2. Find a vector parametric equation of the line segment from the point 1, 2, 3 to the point negative 4, 7, 0. And essentially, if I want to find a parametric equation, well, basically, I have some point in space, I have another point in space, I'm going to draw the line between them, which just really means I need to manipulate the equation of a line somehow, which means I need to remember the equations for lines that we had. Let's see. In order to generate a line, you needed 1, a point. I have 2 of them. Since this is my starting point, that's my point, 1, 2, 3. And 2, I need the direction vector. But if I have the 2 points in my line segment, just find the vector between them, which will be my direction vector. So let's see, P2 minus P1, that's negative 4 minus 1 is negative 5, 7 minus 2 is 5, 0 minus 3 is negative 3. And now that will be my vector, I'll just call it V. And that's my direction vector. Negative 5, 5, negative 3. Now I have a point and I have a direction vector, so I can then generate parametric equations for a line. I think our equations were x is equal to x sub 1 plus at, y is equal to y sub 1 plus bt, z is equal to z sub 1 plus ct. And if I then plug in here, I get x equals x sub 1, 1, plus negative 5, so minus 5t. Y is equal to 2, plus 5t. Z is equal to 3, minus 3t. Now I have parametric equations for the line. Now I can write that as a vector valued function. R of t is equal to 1 minus 5t, 2 plus 5t, 3 minus 3t. And again, I'm not necessarily, while we're calling this a vector valued function and we're writing it in this form, I'm not really doing anything new. I'm just doing what we did in the last chapter. Need a line segment, they're good. So I get my point, I get my direction vector, which gives me parametric equations, which I can just plug in to get my vector parametric equation. So it's really just taking the stuff we've already done and writing it in this form. One thing I will point out, we want a line segment here, not a line. This will give me a line. In order to get a line segment, I need to have values of t that will generate that. But if I just look at it, my starting point is 1, 2, 3. So if t is equal to 0, I get 1, 2, 3. And then where does t end? And I think if I make t 1, 1 minus 5 is negative 4. 2 plus 5 is 7. 3 minus 3 is 0. So if t goes from 0 to 1, this will generate the line segment from here to here. And yes, essentially that means as you're creating parametric equations and then getting a vector function for a given set of parametric equations, you will have to check your limits on t to make sure, again, if you're looking for an infinite curve, then you can just use this. If you're specifically told to find something that starts and stops, then you need to get a starting and stopping value. In class, I think when we were using the helix, we generally did 0 to 6 pi, so we could get 3 rotations of the helix. Sometimes we did a circle from 0 to 2 pi with 1 rotation. So making sure you get this limit is important. But from here, the next thing you could possibly do is maybe say, reparametrize this. And there are different ways to go. For the sake of argument, I will just say that t is equal to 3 tau plus 2. There is my reparametrization, 3 tau plus 2. All I have to do is substitute. So if I substitute right here, we'll say r of tau is equal to 1 minus 5 times t, which is 3 tau plus 2. 2 plus 5 times tau, which is 3 tau plus 2. And 3 minus 3 times 3 tau plus 2. And I can simplify that. Let's see, 1 minus 15 tau minus 10, 1 minus 10 is negative 9 minus 15 tau. 2 plus 15 tau plus 10, 2 plus 10 is 12 plus 15 tau. 3 minus 9 tau minus 6, 3 minus 6 is negative 3 minus 9 tau. And I should have a reparametrization of that, but I have to check my endpoints because now this is in terms of tau, but we can do the same thing. If my original limits were 0 less than or equal to t less than or equal to 1, replace t with that. 0 is less than or equal to 3 tau plus 2 is less than or equal to 1. Now solve. Subtract the 2. Divide the 3. And now, if we wanted to, we could check it really fast. I'll use red to eliminate colors here. Let's see. If tau runs from negative 2/3 to negative 1/3, if I plug in negative 2/3, I get, just for the first one, negative 9 minus 15 times negative 2/3. Negative cancels, that's negative 9 plus 15 times 2 is 30 over 3, 10. 10 minus 9 is 1. So I started x equals to 1. Which is what I want. I'm not going to bother to do the rest of these because all of you can plug in, but the idea is now this reparametrization of this will give me this line segment. I didn't do all of them, but we can see it's starting at the correct x value. If I plug in negative 2/3 here and here, we'll get the same y and z. And if I plug in the endpoint here, I'll get that endpoint. So all things being equal, these parametrizations and reparametrizations are not all that challenging. All we're using is the basic parametric equations, either for circles, helixes, or things we did in the first chapter. Again, parametric equations of line was pretty much standard. We did them for planes as well. But use those parametric equations, which will then immediately give you a function. Just keep in mind what's required. It's already erased. Say if you have a line segment, lines are defined by point and direction vector, so we know how to get that. That leads to my parametric equations, which I then just plug in. Parametric equation for x, for y, for z. That gives me my parametrization. To get another reparametrization, here I use this, but I could have plugged in anything I wanted. Whatever I choose to make, I can just substitute that in for t right here, here, and here, simplify, get a reparametrization, and then the way to check to make sure I did it right is to then change my limits. Again, substitute t for whatever you plug over here, do the algebra, get limits on your new parametrization, your new parameter, plug them in, and make sure you get what you want. If you do, then you know you're right and it works fine. If you don't, then there's a problem and your reparametrization isn't going to work. Admittedly, these things can become really overdrawn and complex. That is not necessarily what we're doing here. All of these parametrizations are pretty straightforward.